In this video we will look at the quantum number of the atom under various approximations. We will specifically focus on the case of LS coupling with a field, which is weak compared to the hyperfine structure. We start with the most simple Hamiltonian you can think of, that of nothing. In this case the energy of the atom does not depend on any of its quantum numbers, hence they are shown here in blue. On adding the central field term, something which I will not go into, the energy becomes dependent on the value of n and L for each electron, hence they are shown here in red. In this case we can rearrange things a bit and write our eigenkits as states of well-defined total L and total S. This is useful since it diagonalizes our next perturbation, the residual field. On adding the residual field term, the energy becomes dependent on L and S and hence they are shown in red. In this case we can rearrange things a bit and write our eigenkits as states of well-defined total J and its projection along the z-axis. This is useful since it diagonalizes our next term, the spin-orbit interaction. On adding the spin-orbit term, the energy becomes dependent on J and hence it is shown in red. In this case we can rearrange things a bit and write our eigenkits as states of well-defined total I and its projection along the z-axis. We can rearrange things again and write our eigenkits as states of well-defined total F and its projection along the z-axis. This is useful since it diagonalizes our next term, the hyperfine structure. On adding the hyperfine structure term, the energy becomes dependent on F and I and hence they are shown in red. Luckily this will diagonalizes our next term, the Zeeman effect. On adding the Zeeman term, the energy becomes dependent on the projection of F along the z-axis, hence this is shown in red. And we are done. You should get the idea by now and understand how to do this for other cases, which is really useful in seeing how things fit together.